Good morning, everyone, and welcome to this lecture. This is lecture number 1 in our newest topic, and the name of the newest topic is capacitance. Have you heard this word capacitance, bacha? Anyone? Anyone has heard capacitance? Yes, what do you mean by capacitance? I've heard about capacitors. Okay, so we use this word capacitance. What do you mean by capacitance of a conductor? Every conductor has a capacity. Every conductor has a capacity to store what? Every conductor has a capacity to store. Books will tell you is the ability to store charge. So we can also write that. That is not exactly very correct. So capacitance of a conductor can be called as ability to store charge. How much charge the conductor can store, that ability or that capacity, the measure of that ability can be called as the capacitance of a conductor. But the better way to understand this is, instead of calling it as ability to store charge, we should call it as ability to store energy. Ability to store energy. A capacitance of a capacitor is the ability to store energy in the form of electric field. So this capacitor or this conductor can store energy. And as you can see, electric field is a potential field. If there is electric field, if there is gravitational field, then there is gravitational energy. Similarly, if there is electric field, then there is electrostatic energy. The ability to store that electrostatic energy is known as capacitance of a conductor. Do we understand this? It's a very simple definition of a very simple and a very good definition of capacitance. Capacitance is the ability to store energy, or some books will say ability to store charge. The next heading that you will write is capacitance of an isolated conductor. Capacitance of an isolated conductor. Capacitance of an isolated conductor. Let us suppose that you have a conductor. Remember, we are now talking about conductor. We have a conductor of any random shape. This is an isolated conductor. Now, I can give charge to this conductor. Let us say I give a charge plus Q on this conductor, and we have seen that whenever we give charge on a conductor, it will come on the outer surface of the conductor. We have seen all the properties of the conductor. Yes or no? Do we remember them, bacha? The charge will come on the outer surface of the conductor. We remember them? Now, if It has been found out that once you give charge to a conductor, the potential of the conductor rises. It creates electric field. The potential of the conductor rises. If I say Q is the charge of the conductor, and if I say V is the potential of the conductor, it has been found out that this charge Q is directly proportional to the voltage or the potential V of the conductor. Charge Q given to the conductor is directly proportional to the voltage or the potential of the conductor. Or I can write this Q equal to C into V, where C is a proportionality constant. And this proportionality constant came to be known as the capacitance of this isolated spherical conductor. This constant C is known as the capacitance of this isolated spherical conductor. Do we understand this?
Yes, sir.
This C is known as the capacitance of this isolated spherical conductor. Since we know that Q is equal to CV, so now we can define the capacitance of a conductor in a different way. Since we know that Q is equal to CV, since we know this formula Q is equal to CV, now I can define the capacitance of a conductor, which is the ability to store charge, or should I say energy. Now I can define this in this way. Capacitance of the conductor, and I hope you can see it now. Capacitance of a conductor is the charge required to increase the potential of a conductor by 1 unit. So you can also now define the capacitance of an isolated conductor in this way. I hope everything is making sense. Yes or no? Are we able to understand this? Or it is getting above our heads? Saying bye bye. Bye bye, I'm going.
Understood, sir.
Okay. Now what type of quantity is capacitance? Scalar or vector? Yes. Is it a scalar quantity or it's a vector quantity? Who is going to tell me? It is a scalar quantity. So remember that capacitance, charge is scalar, voltage is scalar, Q is equal to CV, or I can write from here, I can write capacitance as Q by V is the division of two scalar quantities. So it is going to be a scalar quantity. Do we understand this? Yes or no? No, yes.
Yes, sir.
I'm giving everything point wise beta. Remember them point wise because any of this can come as question in your exam. What is the SI unit of capacitance? The SI unit of capacitance is known as farad. The SI unit of capacitance is known as farad, and never forget its dimensional formula. Its dimensional formula is this: M minus 1, L minus 1, L minus 2, current I or A square T raised to the power of 4. Some books you will find I for current, and somewhere you find A for current. Doesn't matter. I hope you understand this. Yes or no? No, yes. Then comes the question of finding out how much is 1 farad. So you can understand 1 farad would be 1 coulomb per volt. I hope you understand this because it is charge divided by volt. So 1 farad will be 1 coulomb per 1 volt. So 1 farad is the capacitance of a conductor, where if I give you 1 coulomb of charge and you change the potential by 1 volt, that is a capacitor whose capacitance is called as 1 farad. Then we have these commonly used units: microfarad, 10 raised to the power minus 6, nanofarad, 10 raised to the power minus 9, and the friendly picofarad, 10 raised to the power of minus 12. Now, 1 farad may look like a very small unit. Yes or no? You just need to give a charge of 1 coulomb and potential is 1 volt. You have 220 volt in your home. 1 volt is 220 times less than this. 1 coulomb is so little charge. How much is 1 coulomb? 1 ampere for 1 second. 1 ampere current is big, but your AC will draw somewhere around 2 or 3 amperes current. 1 ampere current, a big motor draws around 2 amperes of current. So maybe the charge is a bit much, but the voltage is very less. So 1 farad may look like a very small unit. Yes or no? Yes, a small unit. Yes, 1 farad. What is 1 farad? Okay, we will look at how small or how big a unit 1 farad is. But before going on to 1 farad, let us now understand on what all factors does the capacitance of a conductor depend on. So that is the next heading that you will write. Factors. Factors on which C depend. What are the factors do you think C depends on? Yes, Q is equal to CV, you have seen. What are the factors? And remember these factors, bacha. I've seen questions coming in many cases. Questions are coming from the theoretical part of this chapter, not so much as numerical, but the theoretical part that the questions are more. So just remember all those things that we are discussing here. Each and everything is a potential question. This is not theory. Each and every question is a potential examination question. I hope you understand this. Anyways, the first thing on which it depends on, what do you think it depends on? What is the first factor? Anyone? It depends on the size and the shape of the conductor. You can imagine if the conductor is small, the capacitance is going to be small. If probably the conductor is larger, capacitance is going to be larger. Yes or no? Do we understand this? It depends on the size and shape of the conductor. It is very simple. Now, what is the other factor which influences the capacitance of an isolated conductor? The first is the size and the shape, or you can also call it the geometry of the conductor. So, apart from size, shape, you can also write in bracket geometry of the conductor. Geometry. You understand the meaning of geometry? For example, you have a circular or a spherical conductor, and you have a plate side conductor, you have a triangular plate, you have a circular plate, you have a sphere, alag shapes, different shapes, different geometry, their capacitance would be different. Do you understand this? Yes or no? So size, shape, and geometry, they will come under one heading. The next heading, and a very important heading, is on the surrounding medium. If you change the surrounding medium, and we will be coming across this dielectric constant K. We came across this dielectric constant K, the first class of electrostatics, where we had written 1 by 4 pi epsilon naught. Do we remember that epsilon naught was known as absolute permittivity of space? And then we have written one formula for epsilon naught into epsilon r. And then I told you this epsilon r is also known as K. Does anyone remember this? Does anyone remember that, class? Then I told you this K will come a lot of time, not now, but maybe later on. Does anyone remember that first class, X-Men first class?
Yes, sir.
Yes, sir. Good. Okay. So it depends on the surrounding medium beta. Remember, capacitance depends on the surrounding medium. If you change the surrounding medium, you'll have to remember these terms, because these terms, these things we are going to apply, and we will find out what difference does it make. So all these terms, we are going to see how geometry will make a difference. Everything will come. Trust me, everything will come one by one, and therefore you will have to remember, you will have to remember all these things just for your revision. Remember, this was the class and this was the note that we had written. We had written the force of attraction or repulsion between two charges, and there I had mentioned that this epsilon r is also known as K, where K is the dielectric constant. This was electrostatics, chap lecture number 1. So that same thing has now come. Remember, this is physics, my dear friends, and we never get rid of anything. If something, if a topic is finished, that does not mean that it's not going to come. In the very next class, it might come. So capacitance depends on the surrounding medium. And the third and a very important result, the third factor, and which is going to come just now after our discussion here, is the presence of other conductors. If there are other conductors present, the capacitance changes. So capacitance also depends on whether other conductors are present or not. And we will see that very soon. Don't worry. Let us move on to the next thing. Uh, just understanding on what all factors capacitance depends on is important. But what is more important, and at times it is going to make a lot of difference, on what all factor it does not depend on. And sometimes we get confused. Why do we get confused? And I will tell you why do we get confused. But first, we must first see on what factors it does not depend on. And these are the factors on which it does not depend on. The first factor, it does not depend on the charge of the conductor. That means if you put more charge, it should have more ability. If it has more ability, the capacitance should be more. But no, does not depend on the charge. Number two, it does not depend on the potential of the conductor. How is that possible? Remember the formula that I had given you here. I had said that Q, that C is equal to Q by V. That means it is directly proportional to charge and inversely proportional to voltage. No, beta. It is not like this. This is not the correct way of writing the equation, because the correct way of writing the equation is this way. Q is equal to CV. C is a constant. This C is a constant. Do we understand this, bacha? It does not depend on Q and V. It is a constant. And this constant is known as the capacitance. Do we understand this? It depends on certain factors. What are the factors on which it depends on? I've already told you that. What are the factors on which it depends on? It depends on number one, size, shape, and geometry. It depends on number two, medium surrounding it. It depends on number three, the presence of other conductors. What it does not depend on, and which might confuse us sometimes, is that it does not depend on Q, it does not depend on V, and it does not depend on the energy of the conductor. So if I say conductor has more potential energy. This more potential energy is coming because capacitance is more. It's not the other way around. Do we understand this? Since energy is more, it is more because of capacitance is more. So it does not depend on these three factors. Do we understand this? Yes or no? No, yes. Now we will write the next heading. We have seen the capacitance of an isolated conductor. The next heading is capacitance.
Sir,
Yes, beta.
what is the difference of potential and potential energy?
What is the difference between potential and potential energy? If I put this pen here, it has got potential energy because now it can do work. If the pen is not here, this point has got potential. When I put this pen here, it got potential energy. So potential energy is mass multiplied by potential. In place of this mass, if I put charge, so potential energy, electrostatic potential energy is charge multiplied by potential. Potential is potential energy divided by charge or divided by mass. You understand this?
Understood, sir.
We are sitting inside a gravitational field. You can think it of as electrostatic field. We are sitting in an electrostatic field. This is not a mass, this is a charge. All these points in this electrostatic field have potential. If I put this charge here, it gains energy and now it becomes electrostatic potential energy or gravitational potential energy if this is a mass in a gravitational field.
Understood, sir.
Okay, so the next heading that we are going to go is capacitance of a spherical conductor. Capacitance of a spherical conductor. Now, what do you mean by capacitance of a spherical conductor? I have a spherical conductor. I have a sphere. Now, remember, we are not talking about insulators now. We are talking about conductors. I have a spherical conductor. I have a sphere. And let us say I give it a positive charge plus Q. We have given it so many times. I've given it a positive charge plus Q. And now all of us know this, that this charge will come on the outer surface of the sphere. Yes or no? Yes or no? The radius of this sphere is R. The radius of this sphere is R. Now if I ask you, if I tell you the potential of the surface, remember I told you in the previous class that conductor is an equipotential surface. Potential at all points on the conductor or inside the conductor are same, which is same as the potential of the surface of the conductor. Do we remember this? Yes or no? Do we remember this? Conductor is an equipotential surface. Potential of all points on the surface of a conductor is same as potential of all points inside the conductor. Do we remember this?
Yes, sir.
Now, can you tell me if it is a sphere, spherical conductor, radius is r, charge is q, what is the potential on the surface of the conductor? Does anyone remember the formula for potential on the surface of the conductor? V. Potential on the surface of the conductor. How much was that? Anyone remembers it? Anyone remembers the formula of potential on the surface of the conductor or inside the conductor, inside the sphere, at center of the sphere? Anyone remembers it? I'll give you 2 minutes. to go back, see that formula and tell me. 2 minutes you have. So we remember it. The formula of potential on the surface of the sphere, conducting sphere or any sphere was kq by r. Now the value of k was 1 by 4 pi epsilon naught. And from now onwards, we will not call it k, we will call it 1 by 4 pi epsilon naught because we want to get the answer in terms of epsilon naught. So 1 by 4 pi epsilon naught q by r. Let me rearrange it and write it again. So I can write v as q upon 4 pi epsilon naught r. Yes or no? I can write it like this. So then I can write q as 4 pi epsilon naught into r, this thing multiplied by v, this thing multiplied by v, and I've kept some terms which are shaded with yellow inside a bracket. Now does it remind you of something that we have just now studied? Does it look similar to something that we have just now studied?
Dielectric constant.
Dielectric constant we have just now studied? No. This looks similar to Q is equal to CV, where this entire yellow thing becomes your C, and that is the formula of capacitance for an isolated spherical conductor. The capacitance of an isolated spherical conductor is 4 pi epsilon naught into R. Do we understand this? The capacitance of an isolated spherical conductor becomes 4 pi epsilon naught into R. Do we understand this? Yes or
Yes,
no?
sir.
Pakka?
Akka, sir.
Okay. So this is the capacitance of an isolated spherical conductor, 4 pi epsilon naught into R, where R is the radius of that conductor. Do we understand this? Everyone, will you remember this? And you can see here all the things that we have discussed. What all factor does it depend on? You can see this red radius. Radius means it depends on size, shape, and geometry. Yes or no? Because if the size and shape, if the conductor was bigger, radius was bigger, it depends on the radius. If the conductor was not spherical, if it was of some other shape, R will not come, something else will come. That means it depends on size, shape, and geometry. Do we understand this? Because it depends on R. Do we understand this? Similarly, you can see that it depends on epsilon naught. That means if it is placed in vacuum, it will be 4 pi epsilon naught. If it is placed in some other medium, it will become 4 pi epsilon naught multiplied by k. That means it depends on the medium. So this thing is coming because of the medium. This factor is coming because of the medium, and this factor is coming for size, shape, and geometry. Do we understand this? So whatever we have read is now coming right in front of our eyes so that we can see that clearly. Do we understand this, everyone? Now, since we have known that the capacitance of an isolated spherical conductor is 4 pi epsilon naught into R, can you find out the capacitance of Earth? That is the question. If Earth is assumed as a sphere, if Earth is a conductor, let us assume that Earth is a spherical conductor. If Earth is a spherical conductor, do you know the radius of Earth? Radius of Earth is 6,400 kilometers. Big. Radius of Earth is 6,400 kilometers. Calculate the capacitance of Earth. How much does the capacitance of Earth comes? I'll give you 2 minutes to note this down. 2 minutes. So how are we going to find the capacitance of Earth? To find the capacitance of Earth, I will just multiply the radius of Earth by 1 by 4 pi epsilon naught. What is the value by 4 pi epsilon naught? What is the value of 4 pi epsilon naught? The value of 4 pi epsilon naught. 1 by 4 pi epsilon naught is 9 into 10 to the power 9. So 4 pi epsilon naught becomes 1 by 9 into 10 to the power 9. That is the easiest way to do it. Multiplied by the radius of Earth is 6,400 kilometers. I will multiply it by 10 raised to the power of 3. That will be the capacitance of Earth. And you know it is going to come approximately equal to 711 microfarad. 711 microfarad. That means even Earth, an object as big as Earth, only has a capacitance of 711 microfarad. To have a capacitor of 1 farad, you would have to have a sphere of radius 9 into 10 raised to the power 9, somewhere close to the radius of Earth. Somewhere close to the radius of Sun. Even Sun is not that big. So that means farad is it's a very, very large unit. In fact, microfarad is a very large unit. On Earth, you cannot create the capacitors which will be having capacitance of microfarad, because then you will have a capacitor equal to the capacitance of Earth. So even this capacitance of Earth is taken as infinity for all practical purposes. For all practical purposes, even this capacitance, which is not even 1 farad, is taken as infinity. Do we understand this? Whenever we talk about the capacitance of Earth, we call it infinite, but it is only 711 microfarad. You understand this? Or this has gone above what it's saying bye bye, bye bye, bye bye.
Understood.
Okay, so this is how you can find out. This is how you can find out the capacitance of Earth. And remember, farad is a very large unit. Therefore, in day-to-day life, you will have nanofarad and picofarad coming into the picture. Do we get this? Okay, now since we have understood the capacitance of a conductor, the next heading is potential energy of a conductor. Potential energy of a conductor. Now, since a conductor can store charge, that charge can create electric field, and electric field, wherever there is electric field, there is energy. So you can have a conductor with charge is equal to a conductor which has energy, and the ability to store this energy is capacitance. Do you understand this? The ability to store this energy is capacitance. So from there you can find out the energy. You don't have to understand how this formula comes. You just have to remember the formula. You can write it in 3 ways. Q square by 2C. What is Q and what is C?
Q is the charge and C is the capacitance.
Correct. That is the one formula. That is the first formula. But remember, Q is equal to C into V, yes or no? So if I put Q in place of Q, if I put C into V, I will get the second formula, half CV square. And then if I put C into V as Q, I will get the third formula, half Q into V. If you remember just one formula of energy and you remember Q is equal to CV, all the formulae will come automatically. Do we understand this, what I am saying here, bacha? Do we understand this? Now, this energy is stored in space. So there is one more term that will come, and that may not come as a question in electrostatics, that may come as a question in dimension. Now, this is the potential energy. Now we also have this term which is known as energy density. Energy density. Any energy density of electric field or electrostatic field. So you can write it like this, energy density of electrostatic field. Now what do we mean by this energy density? It is energy or potential energy per unit volume. How much energy is stored in a unit volume, that is known as energy density. So you can write it that energy divided by volume. Do we understand this? Energy divided by volume, and that comes as half epsilon naught, oops, half epsilon naught E square. So whenever you see this term, which term I am talking about, and I have seen this question come in dimensional analysis a lot of times. What is the dimension of half epsilon naught E square? What is the dimension of half epsilon naught E square? So the easiest way to find the dimension of half epsilon naught E square, what is the easiest way to find the dimension of half epsilon naught E square? It is nothing but energy divided by volume. And you know the dimensions of energy. What is the dimension of energy? What is the dimension of energy? And this question comes most probably in dimension. So what is the dimension of energy? Dimension of energy is m L square T minus 2 divided by the volume is L cube. So you can get the dimension of this thing as m L minus 1 T minus 2. This is one of the most repeated question that I have seen, and it has come in exam many times. The dimension of half epsilon naught E square. Remember, half epsilon naught E square is known as energy density, and the dimension is half epsilon naught E square. Do we understand this? Yes or no? No, yes.
Yes, sir.
Okay. Now, this is, we are talking about one conductor only. Now, in many cases, I have seen questions of this drops coming in your NEET exam, where many drops, they combine together to form one big drop. Now, or one big drop breaks up into n number of smaller drops, and this question is very common in electrostatics as well. So we will do that part. This is specifically for your NEET, because these questions basically come in your NEET exam. So you can write the next set, combination of drops, and these drops would be spherical, and therefore we will be dealing with spherical energies, spherical conductors and all that. So we can write combination of drops. Questions on combination of drops. So what do you have? Let us say you have n drops. This is how the questions are framed. You have n drops, each having radius r, capacitance C, charge Q, and voltage V.
Sir.
Oh, you are not able to see. So you will have n drops. Each drop will have radius r, charge C, capacitance C, charge Q, and voltage V. That would be given to you. Then they will ask you what when they combine together to make one big uh, one big drop. What will be the charge? What will be the radius? What will be the capacitance, and so on. We will not get into the theory of it. It is very simpler to understand. The first thing that you have to understand, and you can tell me straight away, if this n charge combined together, if this n drops combined together, what will be the charge on the bigger drop that we create? What will be the charge on the bigger drop? Tell me. It's a straightforward question. What will be the charge on the bigger drop? Q charges, n number of Q charges. When they combine together, the total charge will be n times Q. Yes or no? Yes or no? Do we
Yes, sir.
understand it?
Yes,
Okay.
sir.
The most important factor here is what is the radius of the bigger drop, and this radius will be, remember, the total volume will remain same. So the volume of the bigger drop will be same as n times the volume of the single drop, and therefore you will have this coming in. The radius of the bigger drop will be n cube times the radius of the smaller drop. Now, since the radius has become cube root of n times, the capacitance of the bigger drop also becomes cube root of n times the capacitance C, because capacitance is directly proportional to R, 4 pi epsilon naught R. Do we understand this? Do we understand this? Then we talk about the potential of the bigger drop. You can divide the charge by the capacitance and you will get this capacitance is in the same ratio as the radius. But if you look at potential, it becomes n raised to the power 2 by 3 times V. So you just remember these facts so that you can answer. You can write the answers pretty quickly. The last thing is the energy of this drop. Energy of this drop, you can find it out by half CV square or Q square by 2C, or no matter what. You will always end up with the same answer. The energy of the bigger drop is n raised to the power 5 by 3 times the smaller drop energy. So if you can remember these facts, you can easily find out these facts, not a problem. But if you can remember them, you can do the questions pretty quickly. Have you noted this down, everyone?
1 minute, sir.
Okay, then from my side, the class is over. We have started the chapter on capacitance and we have noted some very important things in this chapter. We have seen what is capacitance, is the energy, is the ability of a conductor to store charge, or more correctly, energy. It depends on the size, shape, and geometry. It depends on the surrounding medium, and it depends on the presence of other bodies. We will see that other bodies in the next class. We have seen the capacitance of a spherical conductor is 4 pi epsilon naught R. The capacitance of Earth is 711 microfarad. Farad is a very big unit, and we have seen what will happen when smaller drops become a larger drop. We will continue with the discussion in the next class. Till then, I will see you tomorrow. Take care. Have a nice day. God bless all of you. Bye bye.